I'm going to continue talking a little bit about the kinds of things that Larissa and Robert Prentner and myself have been working on from a slightly different vantage point. So it's not quite from the same vantage point. It's sort of tangential. It comes out of some of the things that we were working on, and I needed a title for the slide, so for the talk, so I called it Hidden Reality. I don't think it's a great title. You'll see why I called it that later, but I don't know. And it's slightly different than the abstract because I'm the kind of person that just does things at the last minute. So anyway, what I'm going to talk about is Boolean networks, particularly in terms of as an ontology for IIT, and I'll talk about what I mean by that in a second. So as I said, this is work with Larissa and Robert Prentner, and I don't know when it'll come out. It'll come out soon enough, hopefully. I think we still have a few sections in the paper that have to get finished, but hopefully it's going to lead to some additional work in the future. So what do I mean by an ontology? So we were talking about ontology just now and what it means to be an ontology, and can causal power itself serve as that? And the answer is that lots of things can serve as an ontology. Of course, mind itself can be an ontology. In some Buddhist traditions, mind is all that exists. Of course, you have the straight materialists who believe that it's nothing but matter. You have those who believe that the wave function is ontological, and of course those who don't believe that. You could take the Wheeler view that everything is just bits. You could take the Max Tegmark view that everything is just mathematics. You could also take the view that it's all just some kind of a network, and that's and obviously, and there are many others. And I want to say that I am generally a mostly agnostic individual about most things, and so I don't have a particular ontology that I prefer. I think I fall back to some extent on a materialist view. Don't kill me, but you know, I'm very agnostic. I'm open to other possibilities, and I also, while I fall back on that view, I like to tell my students that, you know, there's no way that I could prove absolutely right here and right now that I'm not actually, you know, a Mongolian goat herder or something like that, because I cannot prove that to you. I can't prove it to myself. I could be dreaming this. I could be that, but it doesn't sort of help me operate in the world. So anyway, so in IIT in particular, there's in the 3.0 paper especially, they use a lot of examples that are built on what are called autonomous Boolean networks. They don't actually call them that in the paper, but they are examples of what are known as autonomous Boolean networks. A lot of work on autonomous Boolean networks was done by Stuart Kauffman over the years. And there's some really interesting aspect of autonomous Boolean networks to things like consciousness and agency and things like that, because Kauffman is actually doing it from a complexity, and he does a lot of work with genetics and things like that too. So, but anyway, in these mechanisms, the elements can be on, off, or undetermined, and the mechanisms themselves are usually taken as Boolean logic gates, so OR, AND, XOR, that sort of thing. So an example Boolean network, and this is the example that appears in the IIT 3.0 paper, is that you have an AND gate, an OR gate, and an XOR gate. In some of Kauffman's papers, he uses an AND, an OR, and an OR. And there's an interesting distinction between using an OR and an XOR that has an important implication for quantizing it that I'll get to in a minute. These autonomous Boolean networks are defined by having some number of binary input variables. So in the typical example, you have just two input variables into a given, say, Boolean gate, but there's nothing that says you couldn't have more. This is just it. And there are entities, and then there are also a certain number. And I have to apologize. I mix my my variable letters here, and I probably should have said K for that instead of N. But anyway, the dynamics are determined by the Boolean functions themselves. And it's called autonomous if it's self-contained, meaning you don't have any external inputs. So it's just, in this case, the AND, the OR, and the XOR, their state at a given time determines their state at the next time. And that determines their state at the next time. There's nothing external to the system, so it's called autonomous in that regard. Interestingly enough, and I find this interesting from an IIT perspective too, because, and I will say, and I will admit to Larissa that I am mildly agnostic on IIT as well. I acknowledge that it's certainly the most mathematically well-developed theory of consciousness, but it also has its limitations. And one of the interesting things about it is that these examples, the theory itself is probabilistic, but the examples that they use, these autonomous Boolean networks, have finite state spaces, and so their evolution is actually deterministic. So they're maybe not such a great example to use for IIT because they are deterministic, and at least in theory, IIT is a probabilistic. So, but anyway. So just to give an example of what that means is, so for this particular example, depending on what your inputs are, so if your input is 0, 0, 0, so the AND, the OR, and the XOR are all 0, 0, 0, if it stays in that particular, if it starts in that particular state, it will stay in that particular state unless you perturb it. So unless you randomly change one of the bits. Otherwise, it turns out for this particular set of gates, there's really only two state cycles. And a state cycle is one of these things. I think Kaufman calls them like attractors, but it's you get stuck in a loop, and you just go around and around in that loop, and you could get and I think one of the other reasons that Kaufman uses an AND, an OR is because it has a more interesting state cycle structure than this particular example. There are actually 3 state cycles in that particular example, as opposed to 2. And it exemplifies the idea a little bit more. But once you have a particular input state, you get stuck into one of these cycles and just goes around. So it's completely deterministic. That's the essence of what an autonomous Boolean network is. And so anyone who's read the IIT 3.0 paper will recognize this kind of a thing as just being an example. And I want to emphasize that it doesn't, it's just an example used to illustrate the tenets of IIT. It's not IIT itself, obviously. But the question I'm interested in asking, when one of the things that came up when we were doing our work was we were trying to find, because one of the things that we wanted to do was take IIT into the quantum realm in as faithful a way as possible. Meaning we wanted to really see on a less abstract level. So for example, Zanardi and then Johannes and Sean's paper was on a slightly higher meta level, I think, than the nitty-gritty of workings of things. And we wanted to sort of try to translate it more directly. And so when you do that, you naturally gravitate towards these Boolean networks that are in the IIT paper. And when you try to translate those into the quantum realm, you run into some interesting problems. Some interesting philosophical problems, some interesting practical problems, and some interesting mathematical problems. So to specify, I'm just going to focus on one, just so you get a sense of it here. We're going to focus on the AND operation. So a Boolean operation is a relation between inputs. And I want to emphasize that it's not always sort of defined that way, but one of the things that we found when translating into the quantum realm, because ideally a good quantum version of IIT should recover the classical version of IIT under the conditions of classical inputs, right? Or some other, maybe coarse graining or something like that. You should be able to recover classical IIT from a quantum IIT. It shouldn't be a separate theory per se. So one of the ways that we sort of can talk about it instead is, instead of thinking of the operation as a gate and as a gate existing in a state, we can think of the Boolean operation as a relation between binary inputs. Mathematically, it's given by that map, and I told Tate not to worry about the pointer, and now I'm thinking, well, you can see what I mean. This thing here. So AB goes to AB O plus FA for any arbitrary Boolean function given by that. This is what is just a little bit on the notation here. What does this mean? This means that I have two. So the two here indicates that I have two inputs, two binary inputs, and I have one output. This is just a very general thing. Obviously, that's actually not the case in the example I have. It's really 2 and 2, because technically what I put up there really is sort of in a sense, there's a copy operation there, but classically we don't think of that, right? So technically, classically, we ignore the fact that the A actually does come out. And in fact, if you were actually to build one of these on a circuit board in a lab, you would actually have the A coming out as well. But anyway, and then you have what's called a truth table, which you may be familiar with from 8th grade or something like that. But the truth table just tells you, okay, given the inputs, what are the outputs? The interesting thing is that this particular operation, the AND operation, is irreversible, because it has, and I shouldn't say because, but to give you a simple example of why or how we know it's irreversible, when you look at the truth table, you have two outputs that are identical, 0, 0. So if you have the 0, 0 state, what does that mean? That means you cannot know for certain what the previous state was, because the previous state could have been 0, 0, or it could have been 0, 1. So the operation is it's irreversible. And that's a problem when you want to simulate it with a quantum system, because quantum systems we generally like quantum systems to be unitary, and those have to be reversible. And I want to emphasize too, by the way, that this is what I'm saying here. If you are a quantum person, particularly someone who works in quantum networks or anything like that, none of this is probably new to you at all. I'm not sure anything I'm going to say today is new, but it's interesting to see how it applies to IIT. But anyway, so in general, for any two input Boolean function given by that mapping there is not necessarily unitary. It could be unitary, but it's not guaranteed to be unitary. Okay? However, it can be shown that if you add an ancilla qubit, that mapping is unitary. So in order to simulate irreversible Boolean operations by a quantum system, you have to have ancilla qubits. So you have to have this extra thing hanging around. Hopefully you can already get a sense here of why that sort of introduces some interesting concepts for IITs in terms of some of IIT's postulates, but we'll get into it a little bit down the road here. Specifically, I want to also emphasize that in general, you can sort of generalize this. So Boolean operations, Boolean functions don't have to be 2 to 1, right? You don't have to have 2 inputs and 1 output. You can have any number of inputs and you can have any number of outputs. So for specifically any k input Boolean function, so that would be any Boolean function that took a number of, k numbers of inputs, right? So you could have a Boolean function that didn't depend on 2 inputs. It could depend on 10 or it could depend on 500. And any number of those mapping to any number of outputs, it requires n ancilla qubits in order to ensure unitarity. Notice that this is actually independent of k. It doesn't matter what k is. It matters what n is. You have to have n ancilla qubits in order to ensure unitarity, meaning however many of your outputs that you have. So if your device has 2 outputs, then you need 2 ancillas. And I do want to emphasize that so Larissa showed that example of a C-NOT gate where you have the XOR operation and then you have a copy function. This is kind of ignoring that copy function for the moment. So in that case, it's assuming that there's only 1 output, because in fact, in that case, you really only need 1 ancilla. So, and part of the reason for that is because technically, well, I shouldn't say part of the reason. I would say my feeling is that it's because you can think of it this way, the XOR and the copy are not necessarily simultaneous. But anyway, so this is the essence of sort of the unitarity problem here in terms of how do you address this kind of thing if you're taking these Boolean functions and Boolean operations and you want to turn them into a quantum system. You have a problem because some classical operations are irreversible, but quantum mechanics is not. And so in order to deal with that, you need these ancilla qubits. So this, by the way, this is just for one operation. Okay, this is just for a single operation. Where things get interesting is when you decide, okay, what happens if I want to make a network out of these operations, which is exactly what I've had here, right? So back here, this is just for, say, an AND gate or for an OR gate, something like that. But what we're really interested in is a network of these. So individually, all 3 of those things are, of course, unitary because they all have the ancilla qubit. That isn't. Meaning, you might be tempted to say, okay, those 3 things are all unitary. So I need this extra ancilla qubit floating around in order to take the information from, so I have A and B, and I want to use A and B, and they're going to have some relation between them, say an or an and we're going to copy that onto C, right? Or their output, whatever, they're going to determine the state of C. So then the question becomes, if you have A, B, C, right? Could I take simultaneously B and C? I mean, once A is used up here, I don't need it anymore out here, right? So why can't I copy, say, the information of the relation between B and C over to A, right? Can't I reuse these qubits for different things? And the answer is you can't do that. this is not unitary. You can't do this. This is bad. I suspect, again, I want to emphasize this is very much a work in progress, but I suspect this is related to no cloning. It seems like it would be. But anyway, that's not necessarily unitary. So in general, if you have some m number of arbitrary k input Boolean functions, you need a total of m times n ancilla qubits to guarantee that you will always be unitary. That's an interesting result. That means for this case, so these are all 2 input functions. For that case, I have 3 of these things. I need a total of 9 qubits to simulate this, to guarantee unitarity. Now, it is very possible that there are shortcuts you can take that I haven't found yet, that we haven't found yet, that maybe make things a little bit easier. The details of this are less important than the larger lesson. The fact remains that you need more qubits than you have to simulate. So let's say you want to simulate 3 operations. You need more than 3 qubits. Classically, you don't. You need the same number, but quantum mechanically, you need more. As far as I know, there's no way to do it without more. And that's sort of the takeaway message here. So in fact, the maximum number of qubits in the system has to be that. So you have to have so I say maximum number because obviously this only matters if the operations are irreversible. So the XOR, I said there was a difference between OR and XOR. The XOR is actually reversible. The OR is not. So if you had an AND, an OR, and an XOR, you really wouldn't need, you'd only need 8 qubits. You wouldn't need 9. You wouldn't need that extra one. Anyway, what does this have to do with IIT? So in IIT, we have these transition probabilities that Larissa and others have already talked about. And, if you were to ask, if you were to ask Giulio Tononi what exists, he would say it's TPMs all the way down. The interesting thing about that is that the TPMs, the transition probability matrix, is the rank. So its rank, which is its size, right, is a function of the number of qubits or bits in the system. So classically, if you have m arbitrary k input Boolean functions, the rank of the TPM is 2 to the m. So in this case, you've got 3 2 input functions, and so the rank of the TPM is 8. And that's weird. Well, that's good. There's stuff highlighted on my screen that's not highlighted there for some reason. Oh well. So quantum mechanically, I say it's the no cloning theorem. I don't know that for absolute fact. I think I have a hunch it's related to no cloning. It means that the rank of the TPM could be as large as that. That's a really big difference. That's a huge difference. And it has some implications. So if a quantum Boolean network is the ontology, then a very large multiplicity of qubits are required in order to simulate a classically complex system. In other words, if you have a quantum substrate, if you believe ontologically that a quantum network underlies all of reality, but you believe that IIT offers a good explanation of consciousness, or even if you don't, right? Because this really is agnostic about IIT itself. You need an awful lot of those quantum things, a very large number of them, to simulate classical reality, right? So it's an interesting result, and it raises a few important questions within the context of IIT. So in order to get to this, we have to treat these operations as relations. Do they still count as mechanisms in IIT? What is the mechanism? Right? So in classical IIT, the AND gate, the OR gate, the XOR gate, they are the mechanisms, but they are also in a state. We talk about the AND gate being in a state of 0 or 1. You can't really say that in the quantum case. It's not as cut and dry in the quantum case. And so I think you could get away with saying that they're relations. It does change the way you would treat these things on a level of evolution. So what happens when you evolve them? And that's for future work. It also then brings up the question is what causal role do the qubits play themselves? Meaning, where does the causal power lie? Does the causal power lie? And again, I'm probably betraying my materialist tendencies here. But where does the causal power lie? Does it lie in the relations themselves? And I suppose Tononi would be one who would say that yes, they do, because he's very much a relationalist. And I am sympathetic to that. I will say I am sympathetic to the idea that everything is relational. I think we only define. I think anything, the table, a chair, whatever, is only defined relationally anyway. A table is only distinct in that it is defined in a way that makes it distinct from something else. But anyway, where does the causal power lie? Is it in the relations or is it in the actual qubits? And I suppose, in essence, that's the question of existence within in existence and intrinsicality within IIT. Where is what's the main driving thing? And of course, again, I think Tononi would say that TPMs are where it's at, which would be I guess the answer there would be that it's in the relations. But anyway, it's an interesting question that I don't think we have a clear answer to just yet. But what I find most intriguing, and this is where the title of my talk came from, is these TPMs have this, they have additional ranks, right? So in the sense of, in a classical case, the TPM, the rank of the TPM is it's basically equal to the number of mechanisms you have. I don't know if that can be formally proven, because the mechanisms, I suppose in non-binary systems, things can get very complicated. So I don't really know if that's provable within the mathematical framework of IIT itself. But if you just work with the Boolean networks, the rank of the TPM is the same as the rank of the mechanisms. And again, you'd have to ask, where does the causal power lie? Well, in IIT, a lot is based on the mechanism, right? And so in this quantum simulation of the classical case, you have these mechanisms, and you might only have 3 mechanisms, but you would have the rank of your TPM would be much, much bigger, like really big, like so if you had 9 qubits, okay, then I can't do the math in my head, but you'd have a very, very large number. Like your TPM would be huge. And in fact, Calvin might have been, was it Calvin who did you have the picture of, you had some pictures of TPMs, right? Somebody had pictures of, maybe it was Leo. Okay, so Leo had these pictures of TPMs, and there was one that was really big, right? That's the kind of thing that you would expect for something that might only have three mechanisms, which is interesting. Again, so then the question is where's the reality? What's the ontology? What are, the mechanisms are the relations, right? And so they're the relations, but then are the relations, why would the TPM be larger? So it's an interesting question if there's like a hidden ontology. And I don't mean this, by the way, in the sense of like, I'm not talking about hidden variables in the sense of quantum mechanics or anything like that. I just mean that if you were going to think, let's suppose, for example, you were thinking about, let's suppose that you made a direct correlation to the neurons in the brain, right? I make absolutely no claims about there being anything quantum going on in the brain at all. As Larissa said, it's hot and mushy. It's, there's not much evidence for that. But let's just suppose, right? Or maybe we create some artificial intelligence that's it's a neural network, but it's not hot and squishy. Okay, so everything is just little Boolean things on and off kind of stuff. In this case, if we have a quantum substrate, right, but we're simulating these classical things, we're going to have this huge amount of quantum stuff that's simulating only a few classical things. So by hidden, I mean the fact that you have all of these extra things there that are contributing to what sort of outwardly facing to us, if we are just perceiving a classical reality, we would just see as the outputs of these classical logic gates, right? And so that's what I mean by hidden. And so, as I've hinted, that really brings up this idea of what actually exists, right? What actually exists within the realm of IIT? What is the ontology? And that's something that I don't think has an answer to yet. There's some additional questions that this work raises, including what's the large-scale dynamical properties of these networks. Just like, so Kaufman has his NK model. You can't perpetuate exactly the same way. You can't through time. So you can't evolve these quantum Boolean networks quite the same way through time that you would a classical one, like what Kaufman does with his. And what's interesting is Kaufman finds a lot of interesting implications for complexity and emergence that come out of the classical examples. And so it would be interesting to see what would happen if you did it with the quantum, but there's a different way to do it. And it's very computationally intensive. And I'm working on developing a computational way of solving it, but it's extremely computationally intensive to model something like this, because his NK model, it's not just autonomous Boolean network, it's random autonomous Boolean networks. That means that at each step, the Boolean functions are chosen randomly, and then the inputs are, depending on the setup, the inputs can be switched around randomly, unless it's an n equals k network, in which case every element gets fed by every other element. And the question, of course, is, are there state cycles? Because that would tell you whether it was deterministic or not. The partial answer I have is that in some cases there are not. The system actually, in some cases, evolves towards a maximally mixed state. And it also evolves towards some strange mixed states that I haven't got my handle on yet either. And it all also depends on how you model the measurement part, right? So where does the measurement part come into play? We've been using, just the density matrices, and you can just take the density matrix and then you can take it as the output of the system here and stick it into the system here. But of course, what does that mean, right? because then the other option is, well, you take the density matrix out from the system here, then you make the measurement so that you get a bunch of qubits, and then you send the qubits in. But then, of course, you've lost the information because you've made the measurement. So perhaps, as Larissa suggested, we make a we scan for any, say, entanglement or some other kind of correlated structure, and then we have structure that can't be subdivided. So we have Bell states that are in there, and we find those Bell states or those GHZ states or something, and those get passed on to the next step as a group. You would sort of save some you'd save some information that way. But when you don't do that, you do get these things where they evolve towards maximally mixed states. And of course, I mentioned at what point does measurement actually occur and how does it affect the system? And as Larissa mentioned, it can lead to information loss, and you can get a situation where you can't construct the cause per view of the system. So sort of a major lesson or major takeaway, I would say from this is that, and of course, some of you are going to look at this and say, well, this doesn't even follow from what he was talking about. But either consciousness is it, meaning you're like a member of the mind-only school of Buddhism. That's all that exists. Or consciousness emerges from a very large multiplicity of quantum states. Or something else entirely. But
that's commitment.
Because the person who made me this way is here today, I'm going to blame Matt Leifer for doing this to me. Too many years hanging around him has made me non-committal, even though I'm sure he's now committal. Anyway, I want to say, I'm intrigued by the second part. So the possibility that my gut feeling is that consciousness is an emergent property. Of course, what are gut feelings? They're not worth a whole lot in science, but that is my gut feeling, that consciousness is an emergent phenomenon. My gut then is that the more that you have to have a very large quantum multiplicity, very, very large quantum multiplicity for you to get a conscious system, because of again, this is kind of assuming that IIT is the right model, right? Or that Boolean networks are a good base for it. But I find it's an interesting, intriguing question. Is what does this say about reality? What does this say about the mind, consciousness, and things like that? And so I have a tendency to like the second aspect of that. But of course, I'm always open to other things. So and I think I am just about 5 minutes left. So I'm going to actually leave it open to questions. And I want to thank you. Work is in preparation. It will be out soon. Obviously, we're keen to get feedback on this. And I want to thank Calvin and Marcus again for inviting me. It's great to get on a plane again. So, so thank you.
Questions? Kai, what do you start?
Yeah, so it seems like the idea is to take a classical brain effectively and simulate it with the assumption that there's some ontological substrate that we don't have access to, which is made up of a bunch of extra qubits. So the whole idea is that that whole ontological substrate can only evolve unitarily, it never collapses. That's the goal here?
That's the goal.
But can't you just go to like a classical brain? Because the whole point is that you're just simulating a classical brain, which is going to be like some clockwork machine. You're saying that it's reproduced by this underlying quantum thing, but wouldn't the classical thing already do what you want? Wouldn't it give you the same emergent consciousness?
I'm not an operationalist.
I'm not sure I understand the answer.
Don't you believe in, I mean, just because you don't need the underlying stuff doesn't mean it's not there.
Oh, no, I mean, it's a perfectly plausible explanation, but all you're doing is sort of presupposing a structure, which it's not like that's the source of randomness or free will or something like that. It's just reproducing the thing.
Well, okay, so yeah, so I did leave out some stuff on free will, which there are some issues about free will related to that. So one of the interesting things that I didn't talk about is what, these systems are messy, right? What happens when you have when you introduce noise, or you have so in Kaufman's networks, it introduces perturbations, right? And what happens when you introduce perturbations? And interesting stuff comes out of that. And I think that's where you might get, and again, like I said, this is work in progress, but I think that's where you might get some things that go beyond with just, your standard classical brain. And of course, I mean, this is just one tiny little piece of, I mean, it's a hard problem, as we all know. So, but yeah, it's a valid criticism, but I think the point, I didn't mention the fact that it's the idea of these perturbations. Where do the perturbations come in? And if it truly is quantum, then you are going to have some, perturbations and randomness going on there. And the maximally mixed states that pop up are kind of weird, right? What does that say? And what does that imply for consciousness, right? If you have this system and you keep evolving it over time, and it just keeps evolving more and more towards a maximally mixed state, and this is a chunk of your consciousness, that's kind of odd, or not odd. It may suggest maybe it just suggests that it's not a good model for what's going on in consciousness, which is possible too. So.
Okay. If you guys can just introduce yourselves for the sake of the Zoom audience.
Oh, hi, I'm Spencer Rogers. Yeah, so my question is, would you say that we could have a theory whereby conscious reality seems to supervene on some set of qubits, but there could be some other set that somehow assists in how these other qubits are transforming, like that this on-Scylla set could in a sense be not manipulated and just assisting to be hidden in the background?
So I spent a great deal of time thinking about that exact question. And I don't know. I have not committed to an answer yet. I think so. One of the issues would be, certainly from an existence standpoint, is if they don't, at what point within IIT, for them to exist, they need to have some causal power, right? And so then the question is what kind of causal power do the ancilla qubits have? In some cases, they have a fair amount of causal power, I suppose. And so then, yeah, I guess they would be said to exist. But then, if you need them, if they have to be there, then in some sense, then they must have causal power. And so then they would exist. But it's an interesting question. I don't have a good answer, but it is one that I have thought very long about, and I'm not entirely sure.
Yeah, so I feel like often when we talk about measurements kind of taking a definite outcome, it's like you have these degrees of freedom which are not manipulatable past a certain point. And I'm wondering if these on-Scylla qubits could almost play that.
They could. I mean, so the interesting thing is that when if you take that view, when you sort of perpetuate this or evolve the system forward in time, that that gets into how do you evolve the system forward in time? Because in this classical Boolean networks, right? It's just, you've got the three or four or five things, and they have a state, and then their relation just tells you the next state. But you can't do that in the quantum case. So like you can't even, I didn't put a slide up, but I think Larissa did, where the way we represent these things is not as sort of this network thing. We represent them as sort of these lines, right? And the lines perpetuate forward, and then you have unitary operations on sets of lines, right? And from time step to time step, it's all about connecting the lines and which lines connect to where. Do you have to, for a while, we thought, oh, you have to introduce brand new ancilla qubits at every step. But you don't necessarily. It's just that your ancilla qubits are you would just take other qubits that have been used for something else, and they would get used as ancilla qubits for the next state. So for instance, you could have 9 inputs, right? So 3 ancilla qubits and then the 2 inputs per, right? All going in, and then the 9 coming out, and then you could just randomly assign those 9 to the 9 inputs to the next step. I don't know what that would tell you, but then you could also say, well, okay, the ancilla qubits just never get touched. But the problem with that, though, is that like in a C-NOT gate, right? Or even just in the quantum example of the classical AND gate, the ancilla qubit takes the mapping of the other two, right? The unitarity gets mapped onto that ancilla qubit. So it's not an ancilla qubit anymore. And so it becomes the ancilla qubit in the next step. Right? It's this evolution from one step to another in time that becomes kind of complicated and interesting. You get some interesting structures when you start to think about it. So
You have to worry about erasure or resetting of those entities between steps?
Erasure of what per se?
Well, the ancilla, like, do they need to be 0 when you input them into your protocol, or can they be random?
It can be random. It's 0 by sort of tradition, but it doesn't have to be 0. It can be anything because it erases that. It essentially erases the value of that ancilla, which, by the way, is interesting in and of itself, right? In order to do that, if that ancilla qubit is something, right, and the output, you lose all that information from it, and it's whatever it was, it's not that anymore. Which means, by the way, that if you then use, let's say you have 9 coming out, and you decide to randomly assign these to the next inputs, you have one that say came out as a definite thing here, and maybe it's a bit of information, but it gets randomly assigned as an ancilla to the next step. Then you'd lose any information about what it was in the previous step. And that gets problematic, right? And then because then you have the problem of, well, okay, then how do you construct the cause purview of the system?
Sounds like you've introduced sort of a non-unitary mechanism into this now.
If you randomize, it's very well possible that you do, yes, which would be also interesting.